All right, let's dive right into this. Welcome to this explainer, where we are taking a fascinating look at a topic that honestly feels like it's pulled straight out of a sci-fi movie, but is actually unfolding around us right this second, the quantum technology revolution. You know, we constantly hear about quantum computing, quantum sensors, and how these systems are going to just completely redefine our world. But to make that leap, we really have to look closely at the data behind the scenes. So today we are unpacking a highly comprehensive May 2026 study by researchers Koshimo, Holt, and Talal, titled Program-Level Curriculum Analysis of U.S. Quantum Master's Degrees, Implications for Workforce Preparation. It's an absolutely incredible piece of research that maps out exactly how we are preparing, or, well, maybe not preparing, the very next generation of quantum experts. It's super easy to get completely lost in the hype of the hardware, right? But it begs a pretty massive question. Who is actually going to build this quantum future? It's a pivotal point to consider because our most advanced, mind-bending technological ambitions mean absolutely nothing without the human element. The hardware doesn't build itself, and those algorithms definitely don't write themselves. We need people. The real key here is how we define the quantum workforce. The study lays it out as the specialized human capital required to transition quantum systems from research prototypes to deployable real-world technologies. I want you to notice that keyword, deployable. For literally decades, quantum mechanics was strictly the domain of theoretical lab experiments and, academic whiteboards. Now, we're in an era where we actually need to engineer these systems into real-world applications. And doing that requires a highly specific, highly specialized type of worker.
Section 1, the quantum tech boom. To truly get why this workforce is such a huge deal right now, we really have to grasp the stakes. Quantum technologies are increasingly recognized in the United States as a top-tier strategic priority. This whole thing rests on three massive pillars: economic competitiveness, national security defenses, and technological innovation dominance. The U.S. views quantum tech not just as some cool science experiment, but as a foundational pillar for its future standing in the world. Falling behind in any of these three areas simply isn't an option, and that makes the people building this tech, without a doubt, our most valuable asset. Moving on to Section 2, the workforce preparedness gap. So here's where we hit a massive speed bump. Industry needs are evolving at breakneck speed as the technology races forward, constantly demanding new and complex skill sets. But higher education preparedness is really lagging behind. As the study points out, while prior research has looked at bits and pieces of quantum education, very few studies have actually taken a systematic look at university curriculums side by side with documented industry expectations. And that disconnect is growing fast. Tech companies are practically shouting for specific skills, and universities are struggling to pivot fast enough to actually produce them. Which brings us to Section 3, analyzing quantum master's programs.
The way the researchers tackled this is actually pretty brilliant. First off, they gathered data on the primary U.S. master's programs dedicated specifically to quantum science and technology. Then they used a highly structured coding framework to map out all the course offerings across 6 distinct quantum-relevant skill categories. So they didn't just count the classes, they aggregated the data to produce actual program-level skill profiles. And finally, step 3. They took those university skill profiles and held them up directly against the competencies that recent workforce studies say the industry desperately needs right now. It is a strictly data-driven look at what schools are teaching versus what companies are actually demanding.
Section 4, theory versus practical skills. And the reality check here is honestly pretty stark. Quantum theory massively dominates the curriculum distribution. The study found a really heavy emphasis on theory across basically all the programs, completely leaving applied learning and technical skills in the dust. The research explicitly points out that those practical areas show substantial variability. So what that means for a student is, while you will definitely learn deep theory in these programs, your chances of getting hands-on technical skills or applied learning, it's basically a roll of the dice depending on which specific program you're in. So we end up with this glaring mismatch. On the academic side, the focus is stubbornly stuck on deep quantum theory, but the industry, they are demanding workforce readiness from day one. They absolutely need cross-disciplinary integration because, let's face it, building a functional quantum system takes computer scientists, engineers, and physicists all working together and speaking the same language. When the academic focus is so incredibly heavy on just the theory, it leaves all these critical, practical, and multidisciplinary demands completely unmet. Let's look at some solutions in Section 5, Fixing the Quantum Pipeline. Breaking down these evaluation areas acts as a really precise diagnostic tool. Under theoretical knowledge, we are nailing it. Strong alignment and consistent emphasis across all U.S. master's programs. Great news there. But then we move to applied learning, cross-disciplinary integration, and emerging tech demands. The current status for all three of those? It's a persistent gap. The study explicitly flags these as areas where programs are consistently failing to align with industry expectations. We're looking at a serious lack of hands-on opportunities, insufficient preparation for diverse tech environments, and just a general disconnect from what the workforce needs today. If we don't close these gaps, they are going to become a massive bottleneck for those national security and innovation goals we talked about earlier. There is a huge silver lining here, though, and it's captured perfectly in this quote straight from the study's abstract. This study provides a scalable framework for evaluating quantum education programs and offers evidence-based insights for curriculum design. Think about what that means. What these researchers have handed us isn't just a critique of the system, it is an actual blueprint. Policymakers, university deans, educators, they can take this exact scalable framework right now, evaluate their own programs, and start redesigning their curriculums based on hard evidence to build a truly robust U.S. quantum ecosystem. Which brings us to the ultimate million-dollar question. We have the data, we know exactly what the industry needs, and we know exactly where our current master's programs are falling short. We even have the framework to go out and fix it. But the real question is, can our higher education system actually adapt fast enough to secure the quantum future? Because the technology definitely isn't waiting around, and neither is the rest of the world. It's a challenge that is absolutely going to define the next era of global technological dominance. Thank you so much for joining me for this explainer. I really hope it gave you a clear, structured understanding of the quantum workforce pipeline. Keep questioning and keep learning.